Okay, so good evening everybody. I introduce myself. My name is Yann Girard, and I work in the University just right there. So maybe you know things about tunnel effects, I don't know. But we go beyond that. And the second title of my talk is not seeing the unseen, because we are able to see many things what we don't see. But the thing is more difficult today because seeing what is supposed to exist. And we will see that we believe in something, we believe that things exist. We don't know if they exist, but we have proof, kind of proof that they exist, indirectly. So I will try to expose that situation. My talk, different point, different chapter, 20 minutes to see electrons, in fact. So do you believe that the existence of electrons? This is the point. What is visibly invisible? So I spent not much time on that. Do we see air? Do we see light? Or is it subjective? It is a question. If you close your eyes, you see nothing. If you cut the light, you see nothing. But things are there. Okay? So the next point is the famous scanning technique microscopy. I will try to explain shortly. Then the question is what we observe with this kind of microscope. We observe surface of materials. And the question is, what is a surface? This is a surface, this is another surface, metallic surface. But what is it at the small scale, at the electronic scale? What is it? This is the question. And we will see that electrons are a strange thing, in fact. It's very complicated. I don't know what is an electron, in fact. So chapter 1, what is invisible? So I spend not too much time because I have only 20 minutes. But if you have a question about do we see the air which is around us, the answer is we can see it. By a specific optical situation, we can see air. But here it is not the air. What you see here, it is the sky. It is a blue sky. It is the light coming from the sun through the sky, through the air, moving molecules. And what you see, it is the blue coming from the sun, not from the air. Okay? So this is the point. Second point, which is much more important to understand what is the electrons and beyond electrons, it is this four picture. It is the sun. Okay, this is the sun, but sun which are seen not by our eyes. For example, here it is seen in the visible light. But you can use other instruments to see something else at a different wavelength of the photons. Photons, it's a strange thing too, because their speed is light. They have no mass, and it is waves. So it is very, very complicated, photons, in fact. Sometimes it is seen as a wave, sometimes it is seen as a particle. So this is the quantum world. So I try to explain to you something a little bit about these quantum worlds, about electrons. So this is four pictures, but in different range of photons. One, it is visible. The other one, it is UV, ultraviolet. But you, for your skin, if you tan your skin, you have infrared, and this is X-ray. This is a picture of X-ray emission coming from the sun. And you see that you see different things depending on the energy of the photon you are looking with your specific instrument. For us, our instrument is the eye. But we can do better than that, okay? So you have to understand that you can make a picture of the same thing, but you can see different things of this one. Okay, the sun can be seen in different way with different electromagnetic radiation coming from the sun. So next, are we able to see the heat? So heat, you know, you put your finger on something which is hot, it is hot. You put your finger on something which is cold, it seems to be cold. But what does it mean? And are we able to look that, to see that? By your eyes, it is impossible. By our specific eyes, it is impossible. So the question is, what is heat, in fact? So if you want to understand what is heat, you must understand what is the electromagnetic spectrum. So I have explained this is the visible way, okay, but we are sensitive inside the eye. At the extreme here, it is very long wave. We see for radio, for example. At the extreme here it is X-rays. X-rays can be generated, for example, when you send some particles at very high energy on other particles, there is an explosion of things, atoms, molecules, electrons, and X-rays. So X-rays have a very, very small wavelength. It means that the energy is very concentrated spatially. And that one, the energy is kilometers away. Okay, so this is completely different. All the name of that is photons. So the point for it is a specific range. It is there, infrared. And it is, this infrared is, you see the wavelengths are bigger than the visible light. Okay? So this is why with our eyes, we are sensitive only to this kind of wavelength and not that one. Some animals are sensitive to an infrared, and some animals are sensitive even to a longer wavelength, but not the human. So if we go inside this range of infrared, we can separate this thing. So what is it here? It is the emission of light coming from a body which is at 30 degrees Celsius. And we detect the number of photons coming with a specific wavelength. So you see that you have a big peak here around for this wavelength. It is near the, between the mean wave infrared or long wave infrared, between the two. But you see that if you detect in this direction, you have no photons coming with very small wavelength. Of course, small wavelengths are inside the vacuum, inside the visible, and not inside the infrared. Okay? At the other extremity here, you have less photons coming from with long wavelength. You see, this is the energy here. So this is small energy, big energy. So for a body with at 30 degrees, you have emission of light with this distribution of photons. And what we are able to do, it's magic. We can choose some specific photons to send to a body, for example, on you. And with a specific camera, these photons can come on you and be reflected. And I make a picture of this reflection. I make a photo. And you see that you can make a photo with different wavelengths. As previously with the sun, we can see different things, function of a wavelength we are used to see things. You see? So this is long wavelength, medium, and short. And you see that we don't see exactly the same things. Of course, you can colorize the image at the end, and you can reproduce something like that, which is here, it is emission. And you see the lady has a nose which is cold, colder than the rest of his face. Sometimes it is reverse. People have a hot noise, which is hotter than the rest of the face. Okay? So this is with an infrared camera, and we can see where comes the heat comes outside the people. And here it is rather different. Huh? It is a picture, we irradiate the people, and we collect what is reflected. It's not exactly the same, okay? So the question, what happens? What happens when we send light on the face? So we have to understand what happens when there is interaction between a radiative electromagnetic wave and material. And here, there is many things which happens. At long wavelength, it is essentially atoms which rotate. In infrared light, it is essentially vibration. So when you touch something cold and you touch something hot, in fact, it vibrates, molecule vibrates more where it is hot and vibrate less when it is cold. So it is vibration. At higher energy, you come inside the visible wavelength. So here, in fact, what we see, you send light on something, atoms are excited, electrons take the energy, are excited, and when they disexcite, they emit light. And it is that light that you see. It is that light that you see. Okay, so excitation, electronic excitation, it's for visible light. And even smaller wavelength, so bigger energy, you come in the X-ray, for example, or UV and X-ray, and you can even ionized molecules or atoms. Okay, so the first image of the sun in X-ray, okay, there is some ionization somewhere, and we detect this X. Okay, so what is important here again it is that you can make different pictures for different energies. So right now we come to the scanning tunnel microscopy, and we'll let you this short movie, and I will explain rapidly what happens. So this is the apparatus where I live and I work every day, in fact. And I work here. You see, this is a chip. This is the things which I use to see atoms, in fact. So this tip you can move it toward the surface. And a chip is made of atoms, a surface is made of atoms. And we can apply a potential difference between the two. So the effect of tuning microscopy is based on Nobel Prize in the past. So you see these two atoms, if you polarize the two atoms, if they are with 1 volt, for example, if they are far away, they don't see it together. But if they are close enough, there is this tunnel effect where electrons can move from the surface, from the atom of the surface, to the atom of a chip. And this is a current. The more electrons, the more current you will have. This is the tunneling current. And if you move the tip on the surface, like it is here, if you move the tip on the surface, you can collect this current. And you can have the topology, how the surface is, because you collect the current and you keep the current constant. So if there is a bump close to the tip, you will have a big current. You want that. But if the tip is moving in that direction and there is less electrons below, the tip has to move down to collect electrons. And up and down and up and down. And progressively, you create a picture. Not a picture like the photography I've made before, but here it is a picture pixel by pixel. And you can recreate like that this kind of view. So the point here is that we move a chip over the surface, pixel by pixel, and we collect electrons. Maybe, but is it sure that this thing exists? Is it really a surface? What is it composed? What kind of atoms? The next point is what is the surface at the atomic scale. So here we come back to the surface of gold. So this is the ore. This is a nice crystal of gold. This is the surface of this kind of thing. And if you zoom on it, this is grains, in fact, small grains. If you zoom on it, you will see this kind of tuff, what we see in the geographical place, you know. There is some surface which are flat and steps and flat and steps. This is what we see here. This is the surface of a gold nanocrystals. But if we zoom again, we arrive at a situation, or we see something strange, in fact. You see here it is a zoom on that place, and you see here what we see here. In fact, you have a terrace, a step, a terrace, a step. We flatten everything, okay, to have a better contrast. And what we see here, it is the steps. But here, it is the arrangement, the atomic arrangement of the surface of gold. And we zoom again. You see, you have parallel lines, and we zoom again. This is the two parallel lines. But you see, the scale is very, very small. It's 1 nanometer. This scale, this image is 10 nanometer. It's very small. And there is 525 pixels here, 525 pixels in that direction. 1 minute to make this image. Do we see atoms? Is it atoms or something else? It is periodic, it seems, but there is rumpling, you see? There is a rumpling here. So we have to come back of what is the composition of this gold surface. And of course, it comes from gold. So this is a pictorial vision of something which is completely wrong, in fact. This is not a gold atom, it is a representation. A gold atom is made with a nucleus, surrounded by 79 electrons. And in the mechanic world, in the quantum world, these electrons are stacked at different levels of energies and not at different distance. Of course, they are stacked at different distance, but in fact, the electrons are delocalized all around the nucleus, and we can just say that these electrons has a specific energy. This electron has this specific energy. It is what is represented here. This is different level of energy which are quantized, which are discrete level. It's not continuous. Okay? And if an electron leaves at this level of energy, he has a strange shape, in fact, not punctual. He has a strange shape. He has what is called an orbital. The name here, it is a kind of geometrical orbital. I will show you what it is in one moment. So when you put one only atoms, you have a mass of 79 electrons around. This one is very close to the nucleus, which is positive, so very much attracted. And that one, which is alone there, okay, is rather far away. So he doesn't see the nucleus often, in fact. It is often far away. And he has another shape. Okay. But if we put two gold atoms together, and 3 and 4 and 5 to create an ore, or to create a nanocrystals, it happens something where the electrons interact. These electrons, the one which is there, around like a shell, interact with another shell, with another shell, etc. And in the quantum world, if you cannot say these electrons belongs to that atoms, that one, no. These electrons there could belong to all the atoms constitutive of the material. In fact, the electrons moves around, are shared between all the atoms. So an electron inside a solid, especially the ones which are far away, which are less stuck to the nucleus, these electrons are everywhere inside the solid. Not completely everywhere, because there is something. The nucleus of the crystals are not randomly arranged, but a kind of crystals. So there is a specific arrangement. And the electrons which are delocalized all in the material are sensitive to the nucleus. So this is all these electrons which interact together when we will detect by the tunnel current. Something is strange, because we measure a current, but the electrons are everywhere. What happens? In fact, it's very simple. It is like a photon coming into your eye. When a photon is emitted by light, it moves in every direction. But suddenly, it collapses inside your eyes, and you see light. But before collapsing, it is everywhere. Electromagnetic waves of a photon is everywhere. And it collapses at one moment somewhere, randomly. This is what we call ergodicity, or this is the shot noise for creating image with a photo. The same happens here. Electrons are everywhere, but at one moment, they collapse in a current which flows to a tip, and we measure this current. So what we see like this image, in fact, is the connection of this wave of electrons all together, mixed together, but with the periodicity of the nucleus, and we see this surface. So the point is, for an atom, there is level of energies. For many atoms, there is even more many levels of energies. You see, and for 4 atoms, for example, for each one here, you have 4 levels. And for each one of these energy, it changes in 4 levels when you have 4 atoms. Here in materials, you have 10 power 20 or 10 power 23 atoms together. So all the level of energies are very, very close together. And we represent that not in this way, but in that way. And this is called a bond structure. So when electron leaves at a certain level, there is a certain wave function. If you have another level of energy, you have another wave function. And these electrons are live together at different levels of energy. So this is the surface seen really right now by the STM. So what we see some strange things here. You see waves, in fact. It is this interaction of delocalized electrons which mix together and interact with this defect to create this kind of waves. But what is more interesting, it is that. It is cobalt and copper. Small triangle, we mix together cobalt, they form small triangles, and this is what we see. And if you understand that if you change the energy, the difference of potential between the tip and the surface, you select a specific energy for the electrons coming out, you can see when you change the energy, you see, you change what you see on the surface. When you change the energy, we increase it. You can see that inside there is something which are changing. This is not atoms. This is these waves of electrons at specific energy that we detect, and we detect it with the current. So we can come from orbitals. This is the famous orbital I have said before. This is the bond structure when there is many atoms together with a level which are very, very thin together. Here it is a kind of probability to be somewhere around the nucleus. And on this level, you have a probability to be somewhere with a certain modulation inside the volume of the material we are seeing. So electrons are everywhere. And with STM, we can do better than just see this corrugation. We can choose the energy and make this kind of different images on the same region. Choosing the energy, you can say, okay, I want to see the wave of electrons at this specific energy. And I change the potential, I change the energy. And you can make a slice like that. Okay, and you can choose which slice you are interested in. And for example, these things could appear like that, completely differently. So my job is to understand what happened. And this is difficult. So the last one, it is something which seems to be complicated. So it is graphene on cobalt on silicon carbide. It seems to be very far away from literature, philosophy, and so on. So carbon atoms in a pencil, in the graphite, are very difficult to separate. What is easy, it is in fact to slip away some plane of atoms, a unique plane of carbon atoms. And this is what we call the graphene. Nobel Prize in 2004. So graphene is that kind of thing. So it is only one slice of atom, purely two-dimensional. Okay, it can move a bit, like a sheet of paper. You can turn it. But atoms are together, and they form what is called, you see, this is an honeycomb. Each point what you see here, it's another density of electrons around the carbon atom. And they are arranged like that. Sometimes we see that. We see that because there is two graphene together. So here it is an electronic microscope picture of graphene here on a support. And what you see there, it is graphene, in fact. So cobalt, what is cobalt? So cobalt, this is a kind of cobalt, pure cobalt. And cobalt is magnetic because electrons have something which is called a magnetic moment. And depending on the electrons, you can have an excess of magnetic moment in one direction. This is the case for cobalt. This is why cobalt is magnetic. And the last point is silicon carbide. Silicon carbide is something strange. It doesn't exist on the world. It doesn't exist on Earth. It comes from meteorites. But we are able to synthesize this kind of silicon carbide and even to make wafer of pure crystallites, like wafer of silicon. And there is an electronic based on silicon carbide, and there is an electronic based on silicon. Maybe one day there will be an electronic based on graphene. It is the most studied element of the world, graphene. The most studied element of the world. Not elements, crystals. The most one. Thousands of paper, thousands. So it's very difficult to follow everything on it. It seems to be simple, but it is incredibly rich, in fact. When you mix graphene, cobalt, and silicon carbide together in an intelligent way, you open this kind of image. There is no color, in fact. It's just colorized, okay? So we see many things. It's difficult to understand. So my work is to understand that. But nevertheless, this is a cobalt, flat cobalt. On it there is this graphene, and below all that there is the silicon carbide that you don't see there. Maybe we can see it by transparency. This is the famous, you see there something here with hexagonal shape, the honeycomb is here. So each point here corresponds to a localization of many electrons around the carbon atom. Sometimes it is bilayer like that. We can understand that. But here there is something strange above the cobalt. You see these nice things there? This is what is called a flower defect. And the last PhD student of mine has studied this kind of flower defect. But above the cobalt, look, there is something which is with a rectangular view. You see there? There is this kind of rectangular view. And if you understand that what we see is not atoms, but what we see, it is electrons which interfere together, what we see there, it is this interference of cobalt electrons together with graphene electrons. It is with what we call a nebulization, in fact. And they interact together, and we see that other density which have this rectangular view. And it's very, very strange, because cobalt and graphene have a 6-fold symmetry, 3-fold symmetry. It's completely understandable to make this kind of 2-fold symmetry. So silicon carbide is below because we have, you see, there is something which seems to be periodic. You see the light blue? It seems to be a rather periodic. In fact, it is a moiré. Graphene has periodicity on silicon carbide, which has another periodicity. And when you put two tissues with two different periodicity together, you see that you can see some things which are called moiré, in fact, are very nice. And there is a periodicity inside. This is exactly what we have here. So if I change the energy between the voltage between the tip and the sample, do we see something which is changing? So the question is open for the moment. There is some terrorists which are running some computers to see what happens, in fact. But what we measure is here. And if we change the energy, the voltage between the tip and the sample, we see different things because we see different interference between the waves of electrons. So we move the tip, for example, here. We move the tip pixel by pixel. We have this image. Suddenly, we change the energy, we change the voltage, and we have this image. You can decrease the energy until very small one, 50 millieV is very small. 50 millivolts for an electron, it's very, very small. And in fact, that at this energy, this is the way the electrons are arranged. Completely different than at higher energy. So the question is, you see the rectangle are there. Okay, so the question is what we see here. Why these things happens? And it is difficult because cobalt is magnetic. Graphene, a very specific, strange, for electrons, it's fantastic things, very specific. Interaction between the two can create something new. This is a kind of discovery if we understand. Because we can make research and sometimes we find things, but to find something, it is that we are able to understand what is new and what we see. It is completely different to make only research. I can publish that, but it's not a very good discovery because we have no explanation. But if we are together, maybe you and maybe some friend of me which make calculation, we can understand what it is. And at this kind, it becomes a discovery. Maybe with application, because magnetism plus electrons, it is maybe the new technology. For example, in 10 years, it is already done. You have screens which are stretchable and you can move the screen. Nearly you can take your iPhone or telephone, split it in two, put it in your pocket. Because it is made with carbon organic material. And graphene is one of those. Okay? So you should have some progress. Maybe in 20 years, you will think of this exposure. And maybe these things as application. Maybe. OK, thank you very much. So coming back to visible, invisible, and seen. So this is an invisible conclusion, of course. And this is the last point of this invisible conclusion. So thank you for your attention.